Welcome back, friends. In this video we'll be seeing how to find the normal thrust, radial shear for one of the three hinged parabolic arch. So this is the first numerical example. We'll see this numerical example and slowly we'll complicate the numerical examples, and we'll see how to find and how to analyze this three hinged parabolic arch. Now this is the first example on three hinged parabolic arch. Now here the problem is, for this three hinged parabolic arch as shown in the figure below, we need to find reactions, that is reactions at A and B. So total 4 unknown reactions will be there and we have to find them. Bending moment, shear force, normal thrust and radial shear at quarter span on the loaded portion. So this left side is the loaded portion, which is of uniformly distributed load 4 kN per meter. Now this is the point D, which is at a quarter span in the loaded portion. So on this point D we need to find the bending moment, shear force, normal thrust and radial shear. At all these things we need to find at this point D. So first let us find the reactions at A and B. We know that the pinned supports A and B will carry 2 reactions each. So let me just name them. So I will name this as, say, VA and this as HA. Similarly, I will name this as VB and I will name this as HB. I need to find these unknown reactions first, and then we'll move on to find the other things at that point T. So to find these unknown reactions, since it is a determinate structure, the equilibrium equations which are available with us, that is 3 equilibrium equations, are more than sufficient to find these unknown reactions. First let me apply the first equilibrium equation, that is summation of Fx equal to 0, and my sign conventions will be all the forces in this direction as positive. So in this whole arch there are only 2 forces which are in the x direction, only they are HA and HB. So this HA is in the positive direction, so I will write it as plus HA. HB is in the opposite direction, so I will write it as HB equal to 0. So from this equation I will come to know that HA is equal to HB. Still we don't know what is the value of HA and HB. In the other equilibrium equation, let us try to find them. Next, I will apply the second equilibrium equation, that is summation of Fy equal to 0, and my sign convention will be all the upward forces as positive. Now when I do that, so I will come to know that this VA and VB are upwards, so I will write it as VA plus VB, and this uniformly distributed load is downwards, so I should write it as minus total uniformly distributed load, that is 4, and it is over the span of 18 meters. So minus 4 into 18 equal to 0. So from this I can rewrite this as VA plus VB is equal to 72. So let me name this as equation 1, and let's move forward and we'll apply the third equilibrium equation, that is moment at either at A equal to 0 or moment either at P equal to 0. Let me apply moment at A equal to 0, and my sign convention will be all the clockwise moments as positive. So when I do that, I am taking moment at A equal to 0, so no question of moment of HA and VA. So let us start from point B. So HB also will not come into picture because the line of action of HB will pass through point A. Only VB will come into picture. So VB at A is causing an anti-clockwise movement, so I should write it as minus VB into the total perpendicular distance is 36. Okay. Then so what other force is causing there? So this uniformly distributed load is also there, but that uniformly distributed load at point A will cause a clockwise movement, so I should write it as plus So it is 4 into the total distance is 9. Sorry, the total distance is actually 18. Total distance is 18. So this is the total load, and the perpendicular distance is 9. Right? No any other force is there to take moment at A equal to 0. So I will equate it as 0. So in this equation the only unknown is VB. So I can find the value of VB as 18 kilonewtons. And you're getting positive, it means your VB is upwards. That is, you had assumed it as upwards and it is correct. Now when I substitute the value of VB in equation 1, I can also find the value of VA. So VA is coming out to be 54 kilonewtons, and that is also upwards. So I found both the values, that is both the reactions I found, that is VA and VB. Now let us move further and find the horizontal reactions HA and HB. Now to find HA and HB, what you can do here is, since C is a hinge, I can take advantage of that part, and either I can consider the left portion of the arch or I can consider the right portion of the arch and take moment at C equal to 0 and find out any one horizontal reaction. And you can say that from summation of fx equal to 0, we know that both the horizontal reactions are equal. So when you find one reaction, so the reaction will be easy. So what I will do, I will take moment at C equal to 0, same sign convention, clockwise moments as positive. So I will take on the right hand segment. So when I do that, so VB at C will cause a clockwise movement. VB at C will actually cause, okay, so now VB at C will actually cause an anti-clockwise movement. So I should write it as minus VB, and the perpendicular distance will be 18, right? And HP at C will actually cause a clockwise movement. So I should write it as plus HB into the perpendicular distance will be now the rise 8 equal to 0. So when I solve this, I know actually the value of VB already, and I can find the value of HB easily. So it is coming out to be 40.5 kilonewtons, and I know that HA is equal to HB, so I can say that HA and HB are equal. So this is the first step where I have found all the reactions. So next, let me find the bending moment, shear force, normal thrust and radial shear at a quarter span in the loaded portion.